distortion and intermodulation, spurs and the parasitic suppression for ferrite beads again, and switching type amplifiers, which is class D. Classes are normally recognized as class A, which is the most linear. It comes close to 100% reproduction of the input signal waveform, but it's the least efficient because you have to bias the tubular transistors in the linear region, like about half of the voltage supply. So they're always conducting current, even when there's no signal. So less than 50% of it. Next comes class B, where normally see those in what's called a push-pull configuration. One conductor like the wave. Device doesn't have to be biased to it. Be basically off and then go up to full conduction. So it improves the efficiency quite good. And notice down at the bottom, they're showing the degrees of cycle that it's conducting. So for type A, it's almost time, all 360 degrees of the waveform. The one cycle of the waveform, remember, is 360 degrees phase. And the B is on half of the time, so 180. They came up later with a hybrid called AD. And one of the problems with the type B is you get crossover distortion because of the forward bias offset. Silicon is 0.6, where you've got to overcome that before it conducts. So you have this little band in the middle where you can cross over if either one are conducting. AB, they said it so it's biased one more than 180% of the time, but not as much as a type A. So you have both of those devices conducting at the same time in that overlap region, which reduces the amount of distortion at the price of a little less efficiency. And that was the type B. Then you have a type C, which typically you need, it would be an RF amplifier, you need a tuned circuit. So it only amplifies maybe a quarter of the cycle. And you send that pulse into the tuned circuit at the resonant frequency of the circuit. So cause it to continue oscillating. It can act as an amplifier at a very high efficiency, but a lot of distortion. So you use it in the case where you need a power amplification, you need efficiency, but you don't need a lot of linearity. So you can put up with the harmonic distortion. Then there's a type D. They even say something like T, I don't know what a T is, but basically a type D is a switching amplifier where the input signal is sampled and it generates a pulse of a width proportional to where the input is sampled. So you see this pulse width modulated output. So wider the pulses are equivalent to the higher the voltage. Because now I can turn a switch on and off, generate very high power levels with that. But I have to filter it out, so I have to an integrator carries that back to an analog wave. Very, very, very efficient. Unless you have really good filtering, you're going to get some little bumps and stuff in the wave. Letting the output amplifier on your transceiver separate well, you could be and have a little more distortion. So it depends on whether you want to meet the FCC requirements for the third harmonic. Is what 40 dB down or something in that range. Then in a class A, be a typical transistor class A amplifier. Its bias point is, well, let's say this was DCC was 12 volts, it'd be biased about 6 volts. So it's going to be on all the time, and the input signal is going to cause it to move back and forth across this load line, and the slope of that is dependent upon this RL, and change the amount of current going through it. Therefore, the output. So it can, depending on the device itself, which will have some nonlinearity in it, it can be almost exactly an amplification of the input signal. But if you need a perfect signal, not many other choices. So what's the operating point of a class A common emitter amplifier? And the one I showed was a common emitter, because the emitter was going either directly to ground or through a resistor that generated self-bias. Okay. Well, you follow it. Remember what saturation cutoff is? In a class B, say the input signal is going to two transistors, in this case, one's a PNP, one's an NPN. So one of them is conducting the positive half of the waveform, the other's the negative half, and they miss a little bit in the collector loop. And you see down here, see this little space where it's actually not conducting. But it's basically twice as efficient, I think. I'd say most of your audio amplifiers, stuff like that, is either going to be or maybe, except for the really high-end stuff, the type A, and got big power transformers that get a lot of heat. Class AB is B with the bias change, so it's biased on all the time slightly. It's enough that it's always on, so it's above the cutoff point. That's the basic difference. So it kind of cancels out the effect, the transition from the positive to the negative part of the waveform. So for what portion of the signal cycle does each active element in a push-pull class AB amplifier end up? Class C. Like I said, normally it's going to be driving a tuned circuit, so it's an RF amplifier for a fixed frequency or an analog main of the frequency. If you have to be close to the resonant frequency of that it's only going to basically send a portion of that wave into the tank circuit. In this case, with a single transistor, it's getting one pulse per cycle. That's enough to keep it oscillating at the resonant frequency of the LC. So it makes it much more.
Bob, could you explain what you mean by a tank circuit?
Tank circuit is what we call typically a parallel inductor capacitor circuit. It's kind of called a tank because it stores the energy back and forth between the electrostatic field and the electromagnetic field in those two devices. And if there were no losses, it would just go back and forth forever.
Gotcha. Thank you.
Kind of considered a tank. A Class B amplifier got an input comparative, and you're comparing the input signal with this triangular waveform generator and generating this pulse width modulated output. The width of each pulse, each sample, is proportional to the amplitude. And then you can amplify that to a switching controller and then run it through a low pass filter. It's also called an integrator. And pretty much reproduce the video. So it's the most efficient type. Fairly new, you don't see them very often. Particularly if you're doing high power, the filtering part, you're talking about solid inductors. Okay, so what is a Class B amplifier? Why are switching amplifiers more efficient? So it's either conducting the maximum amount of current with almost no voltage drop, or almost no current, very low voltage drop. So you have very little power being consumed in the device at either point. If it's in the middle, then your power is considerable. What circuit is required for the output of there are multiple of the fundamental frequencies. The higher frequency, twice, 3 times. Low pass filter that only passes the fundamental you're trying to reproduce and blocks all the higher frequencies. Okay. power amplifier, like a linear, at some point, everybody in here will have a external linear amplifier, probably a kilowatt and a half. Depending on how they're designed, they can emit a lot of harmonics. Example is the power amplifier in the cheap, what is it, UV5 album, which I think maybe have improved, but it's got a lot of harmonics. It doesn't really need FCC, I don't think. Oh, I know. But a lot of people have taken that basic design and improved it. They sell it under a different name. They're a lot better, but they don't sell them for 20. Okay, so you care about signal quality, care about harmonics, because the FCC won't approve the device unless the third harmonic is down below. I can't remember the exact number. It's around 40, 42 or I don't know. And they've changed it. Oscillations, because one of the best ways to build an oscillator is to build a high gain amplifier, and it's almost guaranteed to oscillate till you make the changes. And one of the things you can do is install parasitic compressors, which would be some inductance usually, or ferrite beads, to reduce some of the parasitic, or neutralize the stage where you use negative feedback. So it's actually going to reduce the gain of the stage, but it gets rid of the positive feedback that's causing it to oscillate. That's how you make an oscillator, is you keep positive signal. It's in phase with the input, so it enhances the signal. So neutralizing the stage means that you bring some negative feedback, got some negative phase shift in it, so it's not in phase anymore to help neutralize it. So that pretty much will take care of the parasitic capacitance and inductance that is going to be in the output device. That you can't get away from because we're using real world components, inductors that have interturn capacitance, capacitors that have inductance in the lead. So it's not a nice RLC circuit. It's a mini RLC circuit. So basically, you're taking the entire output, phase shifting it, feeding part of it back in. No, if you feed the fundamental frequency back, it's out of phase. It reduces the gain. It doesn't add to it. It also will be feeding back all harmonics too. So you're going to reduce the gain and flatten the response curve. Well, yeah, I mean, you don't get something for nothing. What can be done to prevent unwanted oscillations in an RF power amplifier? What's the answer? Power amplifier, you typically want to use a class A or a B or a linear, because the whole point is you want it to be linear. I really don't know where they use class C amplifiers, but I'm sure they do. Well, actually, I guess FM wouldn't care because you care about the frequency deviation, not the amplitude. Although some receivers have a problem with the FM amplitude barrier, discriminating it. So you're supposed to produce a constant amplitude FM signal. Which of the following is a likely result when a Class C amplifier is used to amplify a single sideband phone signal? Okay. They still have something about vacuum tube amplifiers. And they still make vacuum tube power amplifiers. Actually, a little bit cheaper than the solid state one. And they have tubes that glow nice. And they can keep your room warm in the wintertime. For those, you have a tuning circuit, and you have to tune the output stage that normally feeds into a pi network. It's two capacitors centered across a series of inductors, like pi symbol. And you wind up twiddling two knobs to adjust the grid current and the plate current, and dip them and all that good stuff to get the maximum power out without exceeding the plate current, or the tube starts to turn cherry red. They don't like to do that for very long. You don't have to do all that stuff with a solid state. In fact, a lot of the higher end ones, it's like totally automatic. You just turn it on, it adjusts everything, and away you go. We talked a little bit about the common emitter amplifier. this is what the configuration looks like, where the emitter of the transistor, or if it was a vacuum tube, it would be a common capacitor, is tied essentially to ground. It's an RF ground. There's a capacitor. The resistor is there to provide self-bias to help stabilize the circuit. So you get the grid to be base bias voltage set by this R1 and R2 resistor combination. So it's going to be a voltage divider based on what your input voltage and supply voltage. So if these were equal, say this was 12 volts, it's going to be 6. It's going to be a little bit high. But that's how you set the initial bias voltage to determine where the operating point is going to be. No, this plus is your power supply. N is where your signal is. It's DC isolated from this bias network. So you don't see that voltage back there on the input. So only the AC part of that signal comes through. And if everything works right, it amplifies it. So what type of amplifier circuit is shown in figure E7B? The emitter. That's the emitter. This is the base. This is the collector. So they call it common emitter. That, I guess they call that common source. That's not on the they're all this picture. In E7B, what's the purpose of R1 and R2? That's the base bias. What's the purpose of R3? Double bias. That gives it providing a little bit of negative bias in addition to the R1, R2 bias. And it's dependent on the current, so it's a little bit of negative feedback to stabilize it. Think of how the current's going through there. Okay. And you're going to look at it relative to the base. So relative to the base, it's a negative voltage across that resistor. The voltage, the current is going to create a positive voltage. If it's positive here, it's got to be negative there. I may put a voltmeter across it, switched it. Say this is 1 volt. If I switch the leads, it's going to be -1 volt if I do it in that direction. Well, that's tied voltage divider here. Sometimes they'll even get more complicated, and you'll see two resistors here with a point coming back to even get more of a negative feedback. You also have what's called an emitter follower, or a common collector. Basically, the way to remember it is the output is driven by the emitter. Where in the common emitter, the output came off of the collector. Okay. One of the things about a common emitter or emitter follower, is probably a better way to remember it, because the signal follows the emitter. It has a gain of 1. You can have a high current gain. So it will be a power amplifier, but no voltage amplifier. And it has a low output impedance, so it can it's used typically as a buffer. But you may have an oscillator. Typically, an oscillator circuit won't have very much power output. If you try to draw much power out of it, you affect the frequency of it, even to the point where it will stop oscillating. So you put something like this in between, so you isolate that oscillator from the other part of the circuit, and you can have a higher power output at a lower impedance. So, let's see if it's okay. What is characteristic of an emitter follower or common collector amplifier? Yeah, I would say it's not C. Actually, let me go back. This last statement here, the fact that it's low impedance output, that closely follows the base input voltage. What does that mean? Is the output in phase with the input? Whereas a common emitter is out of phase, inversion. And then we have a grounded grid or vacuum tube. Most of the vacuum tube power amplifiers are a grounded grid configuration. Very simple circuit. Almost all of them use it, so it must be good. It provides a very low input impedance, so you're trying to have it so you can feed it with 50 ohms. You don't have to go through all kinds of matching down in that range to begin with. And you can produce a 50 ohm output, which is what you want. That's a typical circuit. Definitely, you can see where the grid is grounded. And you can have a little tank circuit there on the input as well as on the output. But they're fairly simple configurations. What's the characteristic of a grounded grid amplifier? two main things it did. High power gain in them because they typically no reason to use them. It is high power, but it's not the right answer. And there's no all the above. But the big thing is it's like 50 ohm in, 50 ohm out. Okay, thermal runaway. It's not something you worry about with the vacuum tube amplifier. But the solid state problem. I think I mentioned the fact that is increase in current. It heats up and resistance increases. Old style light bulb with LEDs. If you measure it with an ohm meter, it's very low resistance. So then you put 120 volts on it, and that filament starts going, it increases its resistance. The same thing is true for like any metal. In the case of the semiconductor, and the current increasing, heating effect causes additional current flow. So the more current, hotter it gets, the more current, and it's called thermal runaway. So that's one of the things that you have to prevent in a solid state power. There's current. And fixes, okay? Put that self-light. That helps limit the amount of current that changes current, offset the current. A lot of cases, because the amplifier is non-linear, it can generate what's called intermodulation. We haven't got the mixtures yet, but the whole point of the mixtures, you've got two signals in a non-linear device, they sort of get multiplied, and you get the sum and difference of them. What can happen? Amplifier, non-linear, you get some of that mixing effect with multiple signals in it, frequencies, and you get intermodulation, which are those sum and difference frequencies. You can even get it, I've been told, from a rusty bolt on a tower. It can act like almost like a diode or non-linear device. If you've got RF signals around, it can create intermodulated products that generate at different frequencies. I've never experienced it, but that's what the people that know say. You're shaking your head like you know. Oh, okay. And typically they're the odd order harmonics, third and fifth. Because when you do the sum differences of those, it turns out that's the one closest to the fundamental. So it's the hardest to get rid of. Which this chart always get confused by it. So somewhere we have F1 and F2, which are the two desired outputs. Two different frequencies, slightly separated. And you can see that the third order intermodulation products are going to be 2 times F1 minus F2, or 2 times F2 minus F1. So it's the second harmonic of it minus or plus the other way around. The second harmonic, the one minus fundamental of the other, vice versa. So they wind up very close to the fundamental frequencies. Second order, down here. Third order is over here. This is the two that you really have to worry about. And I think I lied. I think there's a formula coming up. But not yet. But there is one. Because you have to know F2, 2F2 minus F1 and 2F1 minus F2. It's very confusing, but